Okay, our next speaker is Danielle Vigeno, who's going to tell us about large eddy simulations.
Yeah. Thank you so much. Thank you to the organizers for allowing me to talk here. I'm quite new in this community, actually. I've worked a lot in magnetism, but in other astrophysical contexts, so it's really a pleasure to be here. And today I'm going to talk to something that is related to one of the points that were discussed yesterday during the discussion. That is the use of subgrid scale modeling. So I'm going to present some results about large eddy simulations. And my hope is that if somebody is interested in trying to implement some models, some subgrid scale model, then I will give at the end of the talk a simple recipe, just a term that you can add to the induction equation as a first try to resolve better the magnetic field amplification at small scales. This is a bit the take-home messages, and now I'm going to explain a bit the results that we got and why that should work in some situations. So in any scenario in which basically the dynamics at small scales are important, then you should worry about them, of course. So it depends, of course, on the problem, on the model. But if you're in a situation in which, for instance, most of the transfer from kinetic to magnetic energy happens at small scales, then resolution is a key factor. And I'm going to present some simulations that we did in which the main problem is actually the lack of resolution to capture all the relevant dynamics in the system. And the astrophysical context that I'm going to talk about are mergers between stars. So when you have two stars that are merging, you have at the very final in spiral stage, they start orbiting each other. And then when they approach enough, there is a shear layer forming in the interface between the two outer layers of the star which are colliding. And that's a perfect place for a Kelvin-Helmholtz instability, which is a fluid instability that you can have with or without magnetic field, but it's perfect to amplify the magnetic field at small scales. These are simulations by Fabian Schneiders and collaborator. They take massive stars, I think they are O or B stars, and well, they have several sets of simulation in which they show these dynamics, which is very similar to what we see in other contexts. And basically here you see the density on the orbital plane, and here is the magnetic field. The message is that at the beginning, you have this amplification of the magnetic field at the interface, which is dragged around let's say the outer surface, the outer layers of the two stars. And then as they merge, you have a remnant, which at the end becomes pretty circular. And there, the winding mechanism will increase the toroidal fraction of energy compared to the total magnetic energy. Now, I'm going to describe something which is related to binary neutron star mergers. So neutron stars are very compact. It's pretty different in some sense to massive stars just because they're very compact. So when they collide, they do it in a violent way. All the magnitudes are scaled up by many orders of magnitude. And also they're very hard. So really they touch at the very last stage of their spiral. And of course, there is a lot of interest about this because 5 years ago, there was the first event of electromagnetic and gravitational signal coming from such a merger. So there is a huge interest in this for many reasons, related also to fundamental physics. But today, of course, we're going only to focus on the magnetic field amplification. What is the dynamics? It's pretty similar to what I showed before for massive stars, just more violent, just everything is scaled up. Just to give you an idea, when we say we start with a weak field, and weak field in this context means 10 to the 10 gauss. Yesterday we were seeing lunar dynamo with nanotesla, so now you see the orders of magnitude are different. But it's weak in the sense that after this process, you end up with a saturated value that we shall see later in detailed simulation, approach 10 to the 6 Gauss on average, even a bit more. So the dynamics is like this. At the very beginning, you have this shear layer. You have the formation of these tiny vortices. And the Kelvin-Helmholtz instability is very effective at small scales. And the first modes, which are the ones that grow faster, are represented by basically by the thickness of your layer. Now, this thickness in this scenario is very tiny. It's probably below meter. Nobody knows with certainty, but it's much lower of what resolution of what numerical simulation can capture. And I will come back to this in a while. Now, either you do something like this, very detailed. You can see again here is basically with rainbow colors is the density scale, and with red and blue is the vertical component of the magnetic field in the orbital plane. Now, you can see more or less the same dynamics. You have a huge amplification, and then you have these winding effects that tends to create some toroidal structures. But the field remains very turbulent, as we shall see more in detail. Either you do something like this, so something with high resolution for a short time scale. A short time scale, physically speaking, means tens of milliseconds. Or if you want to go to hundreds of milliseconds, that is when the jet is supposed to be formed, and this is related to the gamma ray burst that is going to be launched by the system, then you have to use a much coarser resolution, and that means that you cannot capture the Kelvin-Helmholtz instability. So that means that you have to start with a field that is initially very strong, but has a topology that has nothing to do with the turbulent topology that comes out from the Kelvin-Helmholtz. So basically, there are many results in this sense that are improving, but all of them, there is a big question mark of what is the role of the resolution. And to see this point, this is just an example. So these are 3 of our simulations. Again, the orbital plane with brownish color is the magnetic field intensity. You can see 3 snapshots, but let's focus on the last one after 10 milliseconds. This is what you get with a pretty low resolution. In this case, low means 120 meters in terms of physical scale of your grid. If you increase it, if you double it, now you can see how it's basically the average magnetic field increased by more or less 1 order of magnitude. You double again your resolution, and you again increase by 1 order of magnitude. And this has been seen by us and by all the groups that have worked on this with high resolution. What's the problem? That by brute force, doubling this resolution, you can reach until a certain point. But just to give you an idea, a simulation like this to cover up to 50 milliseconds, which is a good time scale, but it's still short compared to what you would need to get final answers. You need basically tens of millions of hours simulations that are translated in tens of thousands of euros, and probably it's going to increase in the next months, right? So if you want to reach a final resolution that corresponds to the shear layer thickness, then you should, of course, this is not feasible because there is not such a supercomputer memory as a memory issue, but even if you were able, and that will take forever, then you will consume what a mid-sized country like Sweden would consume in 1 year. So of course, brute force is not a solution. And this is why people use, not only in this context, but in other contexts, large eddy simulations. So I'm going to present what we did. This is a series of 5 works so far. You can find the details here. And the idea is, of course, is pretty old. Is okay, I don't reach with my final resolution, then I resolve what I can resolve. And the small scales, I will try to model with some explicit terms that will try to include the effect of the small scale dynamics on the large scales. Okay. Now, this morning, it was mentioned the implicit large eddy simulation, which is something different. So you leave to your numerical scheme to model by itself. So it's a kind of black box in some sense. So it works in some cases. But if you want to have a control on what you're putting here, then you use explicit large eddy simulation, meaning you add some terms into your equation. On a formal point of view, all these can be seen in this way. When you have an evolution equation in a finite resolution simulation, then it's like you're filtering in space your evolution equation. Okay, you are doing some average or filtering. So your continuum field F are split by an average part, which is what you can resolve, plus a residual that is what you cannot resolve. And if you want, that contains the information inside your cell that cannot be followed directly. Now, the point is that when you have an evolution equation, we can cast it in the conservative form. So you have a set of U variables, which are the conserved variables that you evolve, and you have a flux associated to all of them. I'm not putting here sources just for simplicity, because the important thing comes for the fluxes especially. But the same could be applied for the sources. Now, when you have a flux in general is a nonlinear combination of the set of conserved variables. And the key point is that formally in a finite resolution, you take basically you would like to have the average of the flux, okay? But you don't know it, because what you know is actually, it's not the average of the combination of U, but instead is the combination of the average of U. And this is different. So you have some residuals here, which are represented by this term, that, for instance, if this combination is just a product of two fields, then taking the average of the product is not the same as taking the product of the average. And that mathematically means that you are losing some information that is contained within your numerical cell. If it's not clear enough, let's make a didactical example about this with the simplest, probably, fluid equation that is nonlinear, which is the Burger's equation. You filter the Burger equation means that you would like to have the average of u squared. You don't know it because what you're evolving is the average of u. And so this term here, the subfilter term that you are losing, is the difference between the two. And this cannot be known because one of the two is not known. So this is the thing that you want to model by subgrid scale modeling, or by, if you want to use the implicit less, by the numerical scheme. Let's go to compressible ideal MHD. This can be complicated by adding, of course, viscosity, Coriolis, gravity. Let's just focus on this for simplicity. And you can see that already many terms appear. Basically, whenever you have a nonlinear combination in the flux, you have a corresponding term that represents the difference between the combination and the average. We will focus mostly, and we have focused mostly actually, on the induction equation part, okay? So for the induction equation, the flux is basically the electric field, V cross B. Then you can add resistivity if you want. So the information that you lose is this term here. Basically, you lose the product of the average between the components V and B and the average of their products. Now, this is known, of course, by long ago. In this work, we extended it to the compressible IDH MHD. We extended this formalism just with a generic equation of state, so many terms appear. And this could be a good reference if you want to see how all the terms are included. But now we shall focus only on the induction part. Now, historically, the first works to propose how to solve a problem for purely hydrodynamical turbulence was Magorinsky, that proposed the dissipative model. Basically, when you cannot reach the dissipative scales, then you add a term which is proportional to the square of your resolution. And then fine-tuning a pre-coefficient, you can be very accurate in reproducing the cascade with all the properties, statistical properties of your fluid. And that works very well. There are hundreds or thousands of works using this kind of model. The thing is that if you include magnetic fields, of course, this model is limited because here, this model assumes that the only physics you're losing inside the cell is dissipation. So it doesn't allow for transfer between magnetic and kinetic energy, doesn't allow inverse cascade, just allow dissipative mechanisms that you don't see. So in MHD, this will not describe the complete picture of the small scale dynamics. So we use the gradient model. The gradient model has been used in some other context, is known by about 20 years, though the first version are much older, but let's say the application are 20 years old, I would say. It has been used at least in physics of plasma, in engineering application as well, basically fluid dynamics. So we extended it to MHD with an astrophysical context. And the idea is, formally, there is some derivation about this, but the idea is, okay, we said before that having a finite resolution, meaning that you are filtering your field. Now, suppose that your filter is a Gaussian, which is convenient from a mathematical point of view. Then, by derivation, you can prove that you can express the continuous field F as a combination of the derivative of the resolved field. Remember that this resolved field is what you evolve in your equation. So this is something that you know. Of course, you have to truncate it at some order. And what the gradient model does is truncate it at the first order, so that, for instance, the average of a product becomes the product of the averages, plus a term that has some pre-coefficient that is proportional to the resolution. This is an important point, the square of the resolution. And then as a product, scalar product between the gradients of the two fields that you are considering. And that's it. So if you have a product, it's a pretty simple expression. That is what actually you have in the induction equation if you don't have compressibility. This is very important. The pre-coefficient goes with the square of the resolution, meaning that you are not modifying your equation. So you are just adding something that tries to compensate for the lack of infinite resolution. Okay. So in the continuous limit, you recover your original equation. You're not modifying the characteristic speed, for instance. So when you apply to the compressible ideal MHD system that we saw was you have this kind of loss of information in blue, then you come up with this kind of expression in green, okay? And if you look at the induction equation, this is the term that you want to implement. There is a part, which is this one here, that is the ideal part that is there anyway. And then there is this part that if you're dealing with an incompressible fluid goes away. So basically, and anyway, in most cases, this is the dominant part. So I will show you more in detail in the last slide what is basically you have to implement a term like this in your simulation if you want to try it out. Now, what we did is to test this model and other models like Smagorinsky, other models that are basically they put terms that are proportional to the vorticity, for instance. There is a plethora of subgrid scale modeling in the literature. We tested all of them. I have no time to tell you how we assess them, but we assess them in a pretty accurate way. And we recover some results from the literature saying that the gradient model is actually the best in terms of reproducing the small scale dynamics. So we did simulations, first in a box and then in the real scenario, using Symfony the Symfony code. It has a bit the philosophy of Daedalus that we saw in the morning, in the sense that you can write the equation, just write it as if it was LaTeX, and then the program translated them in the discretized version of the equation. You can choose between different numerical schemes, so it's kind of user-friendly. You don't know, you don't have to know exactly all the details of the numerics that are there. And it implements higher order accuracy methods for reconstruction of flux and for time advance. It's in Cartesian coordinates, so it's mostly used for box simulations or for, anyway, situation in which Cartesian coordinates are okay. The box simulation are dealing with Kelvin-Helmholtz instability. So what you have here is a box in which the central part of the fluid goes in one direction, the extreme part of the fluid goes in the other direction. You have an initial perturbation. You start developing at the two shear layer these Carli structures. The boundary conditions are periodical. This is just a slice, it's in 3D. And what you can see, first of all, is that, as I showed before for the neutron star merger case, as you increase the resolution, results change and they don't converge in general, meaning that you increase from the black to the green. If you look at the magnetic energy spectra, which is the dots here, you can see that you double the resolution, and for a given time, you have more magnetic field. If you double again the resolution, it still increases, and it doesn't converge. Okay. Well, at some point will converge, of course, but even with 2000 to the square points, was not converging. You can see how it evolves. So at the end, this turbulence is spread all over the cube, and then it will slowly decaying because we are not putting any forcing in this case. We just let it evolve. So it's basically at the beginning is a kinematic phase in which magnetic field gets amplified, and then you reach a kind of equipartition at small scales. But still, this part keeps growing, and you have some move of the peak of the magnetic spectrum. You can see here the spectrum, well, they have this drop because we are using finite volume methods, so it's not a spectral code, so it's pretty dissipative, let's say, compared to a spectral code. Now, when we play the same game by adding all those terms that I showed you before, the subgrid scale modeling term, these are the results. So now these are the same spectra as before, but now we are including three cases in which we played with the pre-coefficient of the terms of the induction subgrid scale term, and compare the purple one, that is with just 1/8 of the resolution of the green one. So that means that in terms of computational resources is 8⁴ cheaper than the super high resolution one. And you get basically a magnetic spectrum which is really similar. Okay, if you look at the purple one here, it coincides with, in this case, with 1000 to the cube or with the 2000 to the cube. So not only you recover the total energy, the total magnetic energy, but also the shape of the spectrum is very similar. So this is a very good point. And another thing is that you don't see any overshooting. So some subgrid scale models, they don't limit themselves in the sense that you can, they could give too much amplification, while instead here they basically they converge to very high resolution simulations. Now, we play the same game with the binary neutron star mergers, which are much more complicated. First of all, it's general relativistic MHD. So all those terms that I showed before are much more cumbersome, but the idea is the same, and the leading term in the induction equation is the same. And our question is, can we cure the historically known lack of convergence due to the finite resolution that we have? And the idea is we use an affordable resolution, and hopefully we can find results that are numerically convergent, which is something that until recently was never done. And this is actually the results in a recent paper of this year by Carlos Valenzuela and the rest of the group that is based in Mallorca, and myself as well. So here it's a very high resolution simulation where you can see more the dynamics. Okay, again, you can see here when the two stars are merging, you have the development of this shear layer, then the orbital movement drag around the magnetic field here, and then it slowly fills the remnant. The last part to be filled are the highest density part. Just to give you an idea here, the density inside is 10 to the 14 or 10 to the 15 in CGS. So it's, again, it's orders of magnitude away from stars and planets, but the dynamics can be similar to massive stars. And again, you can see how the remnant becomes more and more circular, and the magnetic field becomes more and more intense. That can have local maxima of 10 to the 17, and on average is 10 to the 16 rows. So when you analyze this, besides the visual effect, when you want to do an analysis, then the results are really promising, and we were very happy to see this. Because basically what you see here, okay, you take again a low resolution case in blue, a medium resolution, and a high resolution. And this is the average magnetic field in the central part of the remnant, so where the field gets more amplified. Focus first on the dashed lines, which are without using the subgrid scale model. So you can see a big difference between the blue, the red, and the black. Again, you increase the resolution, and the average magnetic field gets higher and higher. Now, focus on the red one using large eddy simulation, so implementing the subgrid scale model. That coincides basically with the amplification that you get in the high resolution one. Not only that, but if you apply, which is very costly, the subgrid scale modeling to the high resolution one, you don't get a higher result. So meaning that the three are convergent. So it's the best sign for numerical convergence, at least in terms of magnetic energy. Now you look at the same in terms of the poloidal and toroidal contribution, and you still see that the three cases, so the large eddy simulation with medium or high resolution and the one without subgrid scale model with high resolution, are basically very, very similar. See what huge differences we had here, and see how convergent are the results here. And again, this simulation has a resolution which is twice less in resolution, so it's 16 times cheaper in terms of computational cost. So it's quite a lot. You can look better at the spectra, and you can see the same. So you can see among the three, if you look, every line is one of the three cases: medium resolution with modeling, and high resolution without or with subgrid scale modeling. And you can see how the shape of the spectra are really similar. Also in detail, the poloidal and the toroidal one. You can see in particular that in all simulations, the toroidal one becomes more and more important because of the winding mechanism. Now, the other point I wanted to make is magneto-rotational instabilities. That was mentioned a few times these days. And in probably most of you are not familiar with this topic, but there is a recurrent saying that in binary neutron star mergers, you have different effects. The ones that I mentioned already, Kelvin-Helmholtz instability, winding mechanisms. And then a big role is thought to be played by magneto-rotational instability. And the idea is that during the remnant phase, since you have a high differential rotation, then MRI can be very important. Now, we don't see it. We don't see it, and I have a reason for that. Though it goes basically against all what people have taught for many years. So first of all, we don't see it doing a careful analysis because, okay, visually you don't see any clear MRI mode, but that's not surprising because the dynamics is very messy, so you could have a superposition of these modes. But then here's is the amplification of the magnetic field as a function of the distance to the orbital axis. And the region where MRI could be developed because of the basic condition, which is basically the profile of the angular velocity, is after, let's say, 10 kilometers. Now you can see that in that region, you have a huge creation of magnetic field only at the beginning, where the remnant is not being formed yet. So that's just the Kelvin-Helmholtz instability, and this scale represents basically where the envelopes are, where the cores of the star are still rotating. But if you look at the late times when the remnant is there, most of the field is created very close to the axis where MRI cannot happen because there's not the right sign, the omega dr. So we don't see it. And why is like that? Well, because if you go back and look at these dynamics and you remember what are the premises, the theoretical premises for MRI, you need a background field, okay? MRI is a magnetic instability in which you need a background field which is static and large scale. Static and large scale meaning that it moves much slower than the instability, than the growth time of the instability that you want to capture. Now, we have a very turbulent field, so you cannot even define a background field. This is something that, I mean, by definition, you cannot see any MRI growing just because there is not even a background field. It's not like when you set up some box simulations that we saw, I think, 1 or 2 examples these days. You set up a simulation with a background field and then you perturb it and you see these nice channels and that then at the end disrupt the original topology. Here you are not in that situation, so it's not surprised that there are no hints for MRI. And I don't know if I have the feeling that sometimes MRI is invoked, but one should be very careful with what is the topology on which this MRI is growing. Now, this is my last slide, and hopefully this can trigger a bit of discussion among the, well, yesterday there were many people saying that probably this is not needed at all in some dynamo simulation, but if you want to try it out because you think that could be needed to solve some small scale dynamics, this is what you want to implement. I'm focusing only on the ideal part, but the resistive term could be also worked out easily. So you add to the induction equation here, you add another flux. You can put it either inside on the left or right side, depending on how you want to code it. And then you have this term here, okay? Neglecting the compressible contribution. You have a pre-coefficient, and this is the main caveat. I mentioned it before that we have to tune it up a bit respect to what ideally you would like to have 1 if your numerical scheme is 0 dissipative. Now we have to put it quite high, probably because our scheme is finite volume, so it has a dissipation, intrinsic dissipation, and to overcome it, you have to do like this. This is our case. But we would really like to compare this with other codes, even spectral codes. Of course, with spectral code, you have to work it out how to implement it. And I'm very open to any scenario or any code in which this could be tested. So I'm really open, and I invite you to contact me if you want to try that way. So that's it. Let me just say that in our group, that it's a recent group that we are studying at the large extent the imprints of magnetic fields in exoplanets from both an observational and theoretical point of view. So there will be a 3 years postdoc position soon to be open. Probably I will publish it as I go back there. So you are very invited to apply or to spread the voice. Please come to live 3 years to Barcelona. And that's it. I'm done. Ready for questions.
Any questions? Chris? Yes, please.
Could you go a bit about the sort of how you get to this gradient SGS model? Is it related to sort of dynamic similarity arguments? You remember it is basically that. I mean, the assumption is essentially that the small scales are going to be a continuation of the small scale or the small resolve scales, yes, down there. And the C factor you've got to choose essentially gives you how long deep down there you're actually going to go. Is that is basically what is
exactly
That is basically what's
Basically,
going on, yeah.
my interpretation that is not there in the original paper, but if you think about this is a physically agnostic, let's say. So you don't assume anything. Well, you assume what you're saying, that there is a kind of continuation in the physics at small scales.
Yeah.
So it's somehow similar to the high order reconstruction method for the flux, somehow, with the difference that a numerical scheme doesn't care about how the flux is. Here, you exploit the functional form of your flux, okay? But it's basically similar to a reconstruction scheme, so an extrapolation to small scales.
Yeah, okay, yeah. Thank you. Yeah, that's cleared it up for me a bit. Thank you.
What's the gradients? That seems to be important. So it's the gradients that are important here, right? So you compared it with other methods. You said this is the best one because it's a gradient method.
Yeah, well, no, it's called gradient method because of historical reason. Also, the other many times use gradients inside, so they are proportional to the fluid strain, for instance, or to the vorticity. So there are some derivatives. This is called gradient model for historical reasons, but basically because it's a product of gradient. And in particular, for an induction equation, you have the derivatives of B and V. So this one here.
Perhaps you're aware of the work of Matsui and Buffett. I think that they were trying to carry out precisely the comparisons that you're referring to in a Cartesian box. I can't remember, in 2 or 3D, and it actually seemed to work very well, a bit like you've shown us. But then they hit some problems when they went to spherical geometry, added rotation, is my recollection. I don't know if you know that work, but
No.
that's...
But what did they try, the gradient model or?
Yeah, I think so, yeah.
Okay.
I think it looks pretty much like your shortcut there. And I think it worked well in a box, but...
Yeah. I mean, I think it's quite instructive to think about when it's not going to work, actually. I know that may be not what you wanted to hear, so to speak, but no, I think the problem is that if there's new physics comes in the small scales that you're not representing, then you're going to be in trouble. So that, for example, if rotation starts to introduce some small horizontal length scales that are actually coming in underneath where your truncation actually is, then I think you're going to be in trouble then. But of course, I mean, you can try and avoid that kind of problem. So it's quite quite helpful.
It is not magic, okay? It cannot invent stuff. So it tries to extrapolate what is seen as small scales, digging more, a factor maybe 4 or 5 inside the cell. Let's say.
I think we expect that, because of the large magnetic diffusivity, that the scales of the magnetic field are not that small, maybe, but that smaller flow scales and temperature scales and so may play a more important role for the dynamics. You didn't try this, but I guess the same methods would also hold there. Did somebody look at that?
I'm not aware, because as I said, this has been tried. As far as I know, the papers that we started looking at were most really applied physics, physical planets, and so on. In astrophysics, I'm not aware of any other work, at least. I'm not aware. So yes, I mean, in principle, you can take any equation you want. Here I show you what we needed. That is pretty simple compressible idea MHD. But anyway, anytime you have a nonlinear term, you can develop usually it's very easy, because if it's just products, then you end up with products of gradients. So you can add thermal diffusivity, resistivity, viscosity, whatever, Coriolis.
I mean, recently I've also learned that there are machine learning. People use machine learning to get at this problem. Do you know anything about that?
I saw a paper that they implement so they repeated exactly what we did in 2019. They repeated the same, got the same with our model, and then they use some kind of machine learning, but I don't know the details. And they obtain with some a priori test, so without doing the full dynamics, they obtain even better results. A priori tests are, I can spend a couple of words about this, but because we did a lot about this. So a priori tests are like this. You run a very high resolution simulation, and then post-process, you filter it, you take your flux, you filter your flux. So basically you lose some information that you can evaluate within the original scale and the scale you are filtering in. And then you see how this correlates with the values that you get by using the SGS model. And we get something like this, okay? So for the gradient model, you see a very good correlation. Of course, it depends on how much you average. If you average too much, you lose this correlation gradually, but it's much better than Smagorinsky model or other models that we are trying out. And for the machine learning that they tried, it was even better than this. But I don't know exactly what they do. And of course, every time there is machine learning, my big doubt is, okay, maybe when you run at the end, it's super fast and you gain a lot, but how much time was spent in the training part, which is the calibration, no? So, well, you have to be a bit careful about that.
Hi, that was a really nice talk. Thank you for sharing. Have you looked at generalizing this to use more than 2 scales? Like, can you repeat this and get some sort of partial series?
Yeah. We did it. Yeah, we did it. Actually, we went to you mean to the Taylor expansion? No?
Yeah.
So yeah, because you get something like this, so you can go and include the C squared. And we did it because we were seeing that we needed this to put a quite high value of C. And we say, okay, maybe we are losing the following orders. No, we tried it and it didn't improve.
Yeah, you'd think at some point you run into problems if you repeat this over and over again.
I mean, we didn't get any instability, but we didn't see any difference basically with including only the first order.
Oh, I see.
So our main caveat, this is why we would really like to see other people implementing something like this, is because our big caveat that people in normal and also ourselves are a bit worried about is this pre-coefficient that you have to calibrate a bit, and we have to tune it a bit high, no? Like we put usually 8 maybe. I think it's because our scheme is pretty dissipative. It's high order accurate, but that means that it's finite volume still. So I'm really curious to see if you plug it in a spectral code. I expect this C to be order 1, or anyway, maybe not 1, but much lower. So I'm really curious. If somebody is brave enough to try it out, please let me know. We can work it out together.
Sure. Thank you.
So you showed initially that when you increase the resolution of the simulation, or just the normal simulation, that the magnetic field was increasing with resolution, and then maybe there's some sense of saturation at some point. Can you give some physical interpretation as to why you're getting larger field, and also what might be causing that saturation at sufficiently high resolution? Mm-hmm.
Yeah, it's a good question, and we didn't. I mean, I think you should think about it in terms of magnetic tension. I mean, at the end, the magnetic feedback. What we can see clearly is that basically you reach some equipartition at high scales between the kinetic and magnetic energy only at high scales, and this equipartition with time holds on a larger and larger scale. Of course, we didn't do any analysis of the forces or try to decompose, also because it's GR, so it's pretty complicated. But I guess just the magnetic back reaction is strong enough in the small scales, especially, to stop the small scale amplification. But still, there is the winding mechanism that transfer to larger scales. Okay, so you basically you go on and feel this with a bit of inverse cascade a bit. But the details, it's a good question, and it's hard to tell.
Great, thanks.
Also, I mean, here we don't have mentioned that the resistive viscous scales are so long that it's perfectly okay to neglect them. And then there are a lot of other issues more important to worry about, uncertainties both in the physics and in the numerics. sometimes it's pretty hard to understand some details because of the limitation of the scenario.
Any more questions? No? Okay. Let's thank Danielle again. Thank you very much.